Okay, take two. This is sdramThing version 4.0. It is a logic analyzer sort of interface for my analog oscilloscope, and that's what it is so far. Okay, so it takes the SDRAM right here, and the processor, it's an AVR, fills the SDRAM with commands that the SDRAM will then listen to. It will spit them out of its data lines and feed them straight back to its command lines. Command and address, actually. All that data is routed back to it. So after it is loaded with these commands, then it can enter a mode called free running. That's what I'm calling it anyways. I don't know if it exists in another form, but basically once that is loaded with all those commands, then it will run on its own, completely independent of the AVR. So the first thing I'm going to do is power it up. Okay, so now it's powered up, but it's in reset mode right now with this switch, which will be used later. Okay, so now it's blinking. There we go. That means it's loading. Maybe this light is too much. Let's see what happens if I turn it off. Is it still going to be light enough? It's kind of dark. Well, I don't know. We'll see. We'll see. Maybe if I shine it off the ceiling, it'll help. Okay, so right now what it's doing is it's loading the AVR with... Oh, that's not bad. Excuse me, the AVR is loading the SDRAM with the commands necessary to enter free running mode. In addition to that, it's also going to load some just initial data that will be shown on the screen. And what else? I think that's pretty much it. It's a very slow process. It takes about 5 minutes if I recall correctly. And there you go. So, I mean, yeah, you gotta think about it. You know, it's 128 megabytes of RAM. And that poor little AVR is chugging away trying to fill it up with that. So it's gonna take a while. But once it starts, then it will run on its own, so it'll be much faster. In the meantime, I can explain some of the things again. I've already done this once, but the video didn't work. This is the crystal oscillator, which is running at 30 megahertz. That feeds directly into the SDRAM. And it also comes out to here, which is a clock. Oops, maybe that's the reason it didn't work last time. Maybe I bumped something. That is a divider which divides the crystal oscillator frequency by 2 in this case for the AVR. So since the oscillator is running at 30 megahertz, that puts the SDRAM at 30 megahertz, but it's divided by 2 for the AVR, so the AVR is running at 15 megahertz. Let's see. Right now, the AVR is rigged up, as you can see, in kind of a weird way. It's got a separate power connector. It's got a reset switch on top, and I just put a decoupling capacitor on there just for the heck of it. The reason for that is, as part of this demonstration, I will actually remove the AVR while it's running, and I wanted to make sure that that it was in reset mode so that all the pins would be floating. Didn't want to interfere with the free running data, because yes, these lines are fed straight back between the data and the command lines, but they're also, you can sort of see some of the wires are also going to the processor. So when I remove the processor, I need it to be completely isolated when I do that. So we'll leave the power connected to it and we'll put it in reset. So that's that. The next, I guess, piece that I could explain is these guys down here. This is just a flip-flop. This is also a flip-flop, and this is an AND gate and an OR gate. Pretty simple. It's a one-shot circuit because the AVR can only go half as fast as the SDRAM. Those take pulses out of the AVR that are twice as wide as they should be and make them skinny enough for the SDRAM to interpret them. So like an instruction, like the write instruction for instance, would be 2 SDRAM clocks wide, but using this circuitry down here it makes it 1 SDRAM clock wide. So it's pretty simple stuff. It's just a flip-flop and a gate for each signal that needs one, and there's 4 signals that need them. What else do we have? Under here, it's hard to see, but right there is a just a simple bit of logic that's used as a multiplexer, and actually some of those settings can be changed with these dip switches when the AVR is removed. Let's see what else. We've got, these guys are XOR chips. They're from 1980. And I guess maybe it will start up. Let's see what happens. Hey, it almost looks like it worked this time. In fact, it does look like it worked this time. Okay, well, we'll come back to those other chips later. So what we're seeing now is you can see the screen refreshes briefly, and then it pauses for a while, and then it refreshes, and then it pauses. So what's happening is when it refreshes, it is in free running mode during that refresh, and then once it reaches the end, the AVR intercepts it and stops it from free running, and then starts a windowed repeat. So these cursors select a window of data, and that window is repeated 100 times, and that can be seen over here on the oscilloscope right now with better lighting. There we go. So when it's kind of solid like that, then that's when it's refreshing the screen, and when it's pulsing like this, then it's actually repeating the data that's in that window. So the AVR is necessary for that part, but it is not necessary for continuous free running, and that is what I'm going to demonstrate right now. So if I stop it in the middle of a refresh, the free running will continue on its own. So let's see if I can time this. Okay, there we go. Okay, now it's continuously refreshing, which means that it is free running, which means that the SDRAM is completely independent of the processor right now. It is continuously outputting all of its data, and then once it reaches the end, it outputs more of it. It starts over at the beginning. Yeah, it's a little more sophisticated than that, but we'll just leave it at that for now. Okay, so this is part of this demo, is to show that it is completely independent of processor control. So there's my processor. I pushed the reset switch, and so I should be able to remove it from the socket. while it continues to refresh. There we go. And I made this mistake last time, which was to leave it dangling there where it could short out with something. So let's not allow that. It's snagged. That's even better. There we go. Okay. Okay, processor is now almost. Hold on just a second. There we go. Processor is completely removed. Alright. It is running free right now. The SDRAM is doing its thing completely on its own. So that's pretty much the extent of the necessary portion. The other portion of this that I had was we could switch between sample mode and repeat mode still, despite the fact that the processor is not connected, because all it does is select one of two inputs to this multiplexer. And so what's happening is right now the SDRAM is outputting two different sets of commands. One is for read and one is for write, and the multiplexer determines whether it should be reading or writing. Basically it's outputting both sets of commands, but it only feeds through one based on which selection we've got going on. So I can't remember the dip switch settings exactly, but let's see what happens. Yeah, okay. That's not the right one. Okay. Okay, so what it just did was sampled the two leads, which are not connected to anything. So apparently it was high. Red and green make yellow. Two channels were basically floating high, apparently. So now this part of the demo was a little easier when the processor was in. I wonder what'll happen here. So it's not necessary for free running to do this, but I did it just to make it a little easier to see what's happening. So some of the address lines still have the address being continuously output, even though the only time that the address is actually necessary is during the one command, which would be almost impossible to see. So let's see, we've got one. Well, it's power, right? So power. Dun, dun, dun. We should probably see something there. So this should be one of the address lines. Let's try that and see what happens. We'll just do this one. This is the orange wire. I didn't find a red one, but I have an orange wire and a green one, so that's roughly red and green. So let's see what we get here. There we go. Alright. So, probably hard to see, but yeah, you can sort of see it. So this is basically the address changing with the red signal. Wait a minute. Right, with the green signal roughly high the whole time. So let's put the green signal on excuse me, on the next higher address bit. Now we should get both signals toggling when I do a sample here. Let's do a sample. Oops, I guess I didn't leave it long enough. Oh wow, okay. Well, that wasn't quite the pattern I was expecting, but it's kind of a cool pattern. Okay. Well, I'll have to analyze that later, but you can see that there's two channels, red and green. Data is being sampled. Oh, I just removed the leads These were the sample leads. So you can see that the SDRAM is actually still holding the data that it recorded, and now it's saving them. I mean, now it's repeating it. So, yeah. You can also see it on the oscilloscope. That is what's being output right now between the red channel and the green channel. And I'm not sure offhand which one is which. We could probably figure it out somehow. Various numerous ways could figure it out there. Let's see what we got here. We got channel 0 is connected to channel 2 on the oscilloscope, and channel 0 over here is red. So channel 2 is red and channel 1 is green. So that looks something sort of like what we've got on the screen. And what else? Well, there you have it. I don't know what else to say. It's running on its own. It's updating the screen. I can do 2 different modes just by flipping a switch. No processor attached. I don't know. Guess that's it. Oh, I meant to demonstrate sample and repeat with the remote when the processor was attached, but I forgot, so that's okay. I wanted this to be a single take, so I think we got it. Is there anything else I can think of while I'm sitting here on a single take? The only other thing I can think of is part of what makes this possible right now. I'm not using refresh. It's a DRAM, so it's supposed to be refreshed regularly. I'm not using any of the refresh commands that they have for that purpose. They say you're supposed to do it, the entire thing, you're supposed to refresh every 64 milliseconds or something like that. And I've done some experimenting. Like I said, this is version 4.0 here. I started with a different SDRAM. And so I think this is the second one that I've worked with like this. And both of them, 2 entirely different manufacturers, seem to work fine, where even if you only refresh them like less than once every 10 seconds. So 64 milliseconds versus 10 seconds, quite a big difference. And what's happening here is apparently when you refresh, when you open a page and then close that page, that actually performs a refresh on that page. So it's hard to see very well here, but each, yeah, okay, there's a green segment. Wait, no, okay. There's a red segment. So each, it looks like it basically starts, oh, okay, there, it starts there, and it ends there on the first line. It's really hard to see here, but that red segment corresponds to 4 pages, if I have my logic figured out here, because each page, each address location also has 2 bank address bits, so this is actually 4 pages of data. So basically within here, it goes through the first page. That's a burst, which SDRAM is designed to do. It can output the entire page. But then when it gets to the end of that page, then it sends a command to itself to start a new burst at the next page. So the next bank address, basically. And then it does that again, and then it does that again, but once it gets to the last one, then it says, okay, I need to go to a new address rather than a new bank address. So anyways, so in a way you can kind of think of it like it's linear. and then when it reaches the end here, it just continues on to the next line. So yeah, so each time you open a page and close it, it basically refreshes that page, and since the SDRAM is basically outputting its entire contents with each refresh, that means that it's basically refreshing itself in its entirety every time that the screen refreshes. A little confusing. There's the SDRAM refresh and the screen refresh. Those are two different things, but probably getting a little carried away here anyways. So I think that should at least demonstrate what I'm trying to demonstrate. The only other thing I was thinking was maybe I should do a teardown if nobody actually believes that this is actually doing what it's doing. Maybe he's got a processor hidden under that this socket or something. I don't know. Best I could do is take it apart and show you. I'm kind of hoping that's not necessary, to be honest with you. It's kind of a pain. Yeah. We'll see. If it's necessitated, I'll do it another time. Alright. Are we good? What else? Should I sample something else just to make it sink in? Sample 2 more channels here. Let's do a higher address bit, or 2 higher address bits, and see what happens. Okay. How about those 2? Okay, now I'm connected to these 2. Those are 2 much higher address bits. How did I do this before? I don't have that many hands. Let's see, okay. Let's do it like this. Do it like that. Okay, they're not sequential. They're, oops. That's okay. Okay, now let's toggle this guy. Let's see if we can get the screen in there at the same time. Okay, there we go. Oh! Didn't toggle it long enough. Well, that's alright. That's even better. Okay. There we go. Rastafarian going on here. Let's see, okay, so I didn't do 2 sequential address bits. I did 1, and then a space, and then another. So somehow the logic probably works out. Can't think of it right now, but here I am removing those probes just to make sure that it demonstrates that the SDRAM is holding what it's holding. And it looks like I toggled the switch too short, so it sampled there, but then saved what was already in there from the last one. So that's cool. It's actually kind of a good demonstration. It wasn't what I intended, but it's kind of cool. What else? Anything else here that can be used? Actually, you know what? This is kind of cool. Yeah, okay, you can see it. A slight speckling in the black here, and it should be visible as well in the other colors, but it's probably harder to tell. So those are the actual commands being sent. Those are only one SDRAM clock wide, and it's hard to explain it exactly, but the LCD display actually its data is stored serially in the SDRAM, and so each pixel on the LCD represents 7 data locations in the SDRAM, and we're seeing individual pixels here, but it's kind of hard to tell, but what varies between them is their brightness, and that corresponds to which bit in the serial data stream is active. and I think if I have this all figured out right, then each one of those pixels that we see here is actually only 1 bit active in that yeah. I'm having a hard time phrasing it. But anyways, those are the commands. And if it was possible to see two commands on the same line, it would be really, really difficult to do with this camera. That's the whole reason for the cursors, which can't be moved right now because that does require the microcontroller. But if I could move those cursors, for instance, to one line of the pixel data up here, then we could actually zoom in on those commands and actually see what they look like. But we can't do that right now because there's no processor. That's kind of cool though, I kind of dig it. Alright, well, let's see what else. That was added by the processor. 4608 is the number of pixels between the two cursors. So it's roughly, not quite, but almost 4 lines of pixels. Or maybe a little bit more. And anyhow, the cursors can't be moved because there's no processor. Right? No processor. Okay. I think we made our point.